giving us the venue here. I do have an idea that I want to kind of bounce off people here that are kind of tech and future oriented, is I would love to also have a monthly futurist meetup here in Austin. It's something that we had for many years in Los Angeles and was really fun, talking about what are the latest developments in, nanotechnology, aging, medical research, all sorts of different areas. So if any of you are interested in that, it's not something I want to kind of have to carry by myself, but I would be looking for somebody who's interested. Okay.
I think there's some other features folks around.
Awesome. Great. Yeah, if you can ping me, I think it'd be really cool to have that, and maybe the Capital Factory might host that as well, or we'll find something. But I think it would be really cool because there's just a lot of good stuff happening, and a lot of it is really interesting. I mean, space and everything to do with futurism. Okay, let me get started. Yes.
I just found a comment that somebody, Mike Archibald, was wondering if there's a video.
What's that?
Is there a video? Is it streaming?
It's supposed to be, yeah. It's supposed to start streaming at 5:30. So there's a link in the invitation, so you could actually. Yeah. Actually, if you can confirm that the streaming is working, that'd be good.
It's working.
Well, I'll just have to hold the microphone a bit closer. Everybody here okay? Yeah? Otherwise, lots of space in front here. My talk is primarily about cognitive AI and what that is. It's probably a term you don't really know. It might be confused with cognitive computing that IBM butchered, a decade ago or so. But what I really, every time I give a talk, I do want to take a bit of time to talk about really what AGI is, because I think there's a lot of confusion about that. I think the easiest way to talk about it is to talk about what AGI would do for us when we have it. So imagine having an AI that is trained up to be a cancer researcher, PhD level cancer researcher, and an AGI would be able to train itself much like a human. It would kind of hit the books and obviously get some coaching and training and so on. But you could have an AGI PhD level cancer researcher. Now you can make 1 million copies of that and have 1 million PhD level cancer researchers chipping away at pursuing different avenues and sharing findings and so on. I mean, that'd be pretty awesome. And you can have that in every field, whether it's energy, battery efficiency or pollution or, longevity or whatever field you have. That would be the power of an AGI. Now, also, any desk-bound job can be automated with AGI. It would be a massive reduction in the cost of goods and services and really create radical abundance by reducing the cost. Now, the third area that I'm particularly keen on is if we each had what I call a personal assistant, basically a personal assistant that we own. It serves our agenda, not some mega corporations. So it's the first personal. Second personal is it's hyper-personalized to you. It gets to know your history, your goals, your wishes, your plans, and what you're all about, and can help you in life. And the third personal is, of course, the issue of privacy, that you control what it shares with whom. And having such a personal assistant that really on an ongoing basis learns more and more about you, I think will really help optimize our lives. We'll make better decisions. When we have to make, whether they're small or big decisions in life, we can bounce them off our personal assistant, and it can help us think things through. It's a bit like having a little angel on your shoulder, that can help you make good decisions. So that is what AGI is. To have that level of intelligence that it can really learn like a human, only better and more rational. As I talk, it's like a human. There are, of course, inherently a whole lot of benefits in having a computer think and reason and learn. One of them is a lot cheaper than humans, potentially. It communicates much better, so if you have these scientists, they'll be able to share information much more effectively than humans. Also, they don't have egos getting in the way. They work 24/7 with full concentration. I wish I could fully concentrate, even 10 hours a day. And they don't have certain distractions, that we enjoy. And, they have photographic memory. They have all the access to all the information in the world sort of really plugged in. They can just essentially think about something and have the information. And they're much better at logical thinking than we are. Because rational thinking is kind of an evolutionary afterthought. We're not really that good at it yet. So now, this is why people say this is the right kind of approach to AGI. Yes, AGI will be bigger than the internet, will be bigger than electricity. It'll be a radical invention. Now, then you have people like Sam Altman, who abuse the term, mangle the term. I don't know if it's for marketing reasons to try and raise money or whatever, but to say, oh, we'll have human level, we'll have AGI soon, but it's really not going to be such a big deal. Well, that's not AGI. So how can we get to AGI? ChatGPT sort of gives us a taste of what this might be like. I mean, with the amazing conversations you can have, far better than we've ever had before. But yet it's still so far away. So how can we get there? Why don't we have AGI yet? What's in the way? So a good way to look at it is what DARPA calls the 3 waves of AI. I think it's a useful model. The first wave is basically all of the stuff that was done in the 70s, 80s, 90s, now called good old-fashioned AI. So those are kind of logic-based approaches, expert systems, Deep Green, Deep Blue, IBM's Deep Blue would be an example of that. So that's the first wave. The second wave, of course, is the one we're riding right now, that hit like a tsunami about 12 years ago, when people figured out how they could use massive amounts of information and massive amounts of compute to really do interesting things with neural networks. And that's the wave we're still riding now with generative AI, which is just a development of these fundamentally statistical big data approaches. And what DARPA mean by the third wave is cognitive AI. So what is cognitive AI? It's really, if you think about it, it's starting with the question of what makes human intelligence special? What is human intelligence? And that's the starting point. Not, we have a lot of data, we have a lot of computing power, what can we do with it? It's really to solve the problem of human cognition. And what some of the quick things, and I'll go into more detail, is that we can learn incrementally and adaptively. So we can change our minds, we can take new information, and we can do this conceptually, we can generalize, and we can do that in real time autonomously, basically by ourselves. We don't constantly need a human in the loop like you do in LLMs. So, those are kind of the fundamentals you have to start with, to say cognitive AI has to be able to learn incrementally and be able to learn and think conceptually and to be able to do that by itself. So another big misunderstanding of intelligence is a lot of people conflate knowledge with intelligence. People think that if you have a lot of knowledge, so then you have a lot of intelligence. But that's not the key. The key is the ability to learn new knowledge and to integrate it and to be able to use it and generalize it. So it's really the parts of the brain that allow you to acquire new knowledge and skills. That is the key to intelligence and to building AI that has intelligence. Now, you can immediately see that large language models are sort of the opposite of that. It's the brute force getting a lot of knowledge and skills into this model, but not the actual mechanism for learning incrementally. So a couple of different ways, again, to distinguish a cognitive approach is, as I mentioned, the first one is the difference between having knowledge and the ability to acquire knowledge. The second one is whether you have kind of a narrow or fixed domain that you're applying, which is really what AI has been about now, where you pick a particular problem you want to solve, and then you have external intelligence. It's really the programmer's intelligence, the data scientist's intelligence that solves the problem, that figures out how to program the system, how to tweak parameters, what models to use, or whatever. And I think that's often overlooked, that you think with LLM, well, the intelligence is in the LLM. No, to actually get it to do useful things in the real world, it's the human ingenuity that's needed to put it together. And currently it's always focused on solving a particular problem that you're zeroing in on. And that's ultimately not what flexible general intelligence is about. So, that the last bullet point there is, again, this idea of the intelligence really being external rather than internal. So one more way to look at this is if you plot this as something that is fully adaptive, that can basically learn new things and adapt to changing circumstances and so on. And on the other hand, with a human you need a human in the loop. Right now, the models that we're working on are really at the bottom left quadrant, where we want to end up as the top right quadrant. And this graph, again, characterizes what the difference between LLMs and a cognitive AI approach, where your focus is on real-time autonomous adaptive conceptual learning and reasoning, as opposed to having a lot of knowledge and skills. And so it doesn't matter how much you scale the LLM, how much more knowledge or skills you give it, it's not going to get to where you want to get to, the human-like intelligence. So here's a summary, and it's a bit of a laundry list of things, and I'll share the slides as well. Don't have to go through them again right now. But the focus is on accessing existing knowledge versus acquiring, statistic versus conceptual, training time in real time, instantaneous training supervision. One thing I haven't spoken about yet is the lack of metacognitive thinking in statistical models, what Daniel Kahneman calls system 2 thinking. So our brains is a good model where you could basically separate out subconscious automatic thinking, or what he called system 1 thinking, which is, when we're driving a car, nothing is happening. It's like we're not even aware of it, and it just happens. But then, something happens, and system 2 kicks in, where we need to actually make sense of something. We need to think about it, and maybe activate some other responses or some other knowledge. And real intelligence very much has that metacognitive component, the ability to think about thinking, to be aware of the thought process, to be aware of how certain am I about something? Is this new? Is this surprising? And so on. So emotions, cognitive emotions, are very much tied into this metacognitive process. Yeah. We have cognitive models running on 5-year-old laptops. You know, we don't need to spend $100 million to train a model. I mean, we also don't have 10 trillion bits of information in our models, but you know, you train the model for what you want it to do. It can basically learn, I should say, teach the model rather than train the model. Hallucinations inherently, because it's not fundamentally statistical, kind of guessing the next word approach, it doesn't suffer hallucinations. And it is inherently scrutable in the way it's implemented. Okay, so I think I've already probably given you enough clues of why I don't believe LLMs can get us to AGI. But let me spend just a bit of time here. And in fact, Jan LeCun yesterday made the statement, so this is hot off the press, on the path towards AGI, an LLM is basically an off-ramp, a distraction, a dead end. And I think it's a very profound statement, and I think very clear that if AGI is the goal, then any effort put into LLMs, into statistical systems, is probably a waste of time. Even Demis Hassabis, now he's been trying to build AGI for 10 years with a virtually unlimited budget. He has, I don't know how many today, but he had, I think, 600 PhD level researchers chipping away at the problem. But if you're using the wrong approach, it doesn't matter how much money you throw at something. You know, if you're trying to get up north, and you're pointing this direction, it doesn't matter how fast you go or how far you go, you're not going to get to the destination. So, you know, Demis Hassabis realizes that their approach is not going to get them to where they want to be. Now, do they have answers on how to get there? Not really. And the reason for that is because they are not thinking about the problem from a cognitive perspective. They're thinking about the problem from a mathematical, statistical. That's their background, that's their training. And until they really reboot and say, we have to think about the problem, the starting point has to be, what does intelligence require? What is important in the kind of intelligence that we're looking for in AGI? And then you have to build systems that meet those requirements. And you know, big data, backpropagation, those kind of approaches are inherently the wrong approach. So the last time I gave a talk here was actually specifically focused on this topic of can LLMs get us there? So I don't want to repeat that. I want to spend more time expanding a little bit on how we're going about with cognitive AI and give you a bit of a better understanding on what I think cognitive AI should look like. But, you know, inherent limitations, hallucinations, inability to learn in real time, black box, not auditable, limited understanding, no metacognition, and extremely expensive, which actually is now starting to become quite apparent. We are seeing a lot of enterprise customers that have spent the last year trying to implement LLM-based solutions or ChatGPT-based solutions, and they're abandoning that. We're seeing a lot of companies abandoning it because they're finding not only is it not reliable enough, but it's also actually very expensive, and in some cases ends up being more expensive than whatever alternatives you have. Often they are much simpler traditional AI or computer science solutions to what you're trying to solve. Yeah, the name already gives you a good indication of what the problems are. So, you know, people try to deal with these limitations by a whole lot of external things. You know, you basically have an input buffer that you put in, you do fine tuning, you have external databases, you know, RAG, and layers and layers of extra things to try and make the LLM work. But in many cases, you end up with kind of the tail wagging the dog, saying, well, if you have all of this other stuff around there to achieve your objective, how much is the LLM actually still doing? Do you still actually need it? All right, so I guess you're not surprised that I say that it's not fixable. So, Sam Altman went from attention is all we need to $7 trillion is all we need. So I guess they're still looking at that. But imagine having a powerful AI that costs a tiny fraction of it, can learn incrementally, doesn't hallucinate, and is auditable, is not a black box. How is that possible? So this is where I want to go into more detail of what this cognitive architecture can look like. So cognitive architectures have actually been around for quite a while, but they haven't worked very well for a number of reasons. But then again, neural networks had been around for decades and they didn't work very well until somebody figured out how to make them work well. So cognitive architectures traditionally have had different modules for things like language understanding, for reasoning, and then short-term memory or long-term memory, and they had all these different modules that didn't really integrate and talk to each other very well. And then, of course, we had the limitations of simply the computing power of 30 years ago or 40 years ago just wasn't quite there. So a cognitive architecture, I believe, is the way to go. And small data learning algorithms inherently having algorithms that can learn, that do true one-shot learning. A child, you can show a child that's never seen a giraffe before, you can show a child a picture of a giraffe, can now recognize it, from the side, from the top, with purple spots or whatever. With statistical systems, you probably need to give it a few hundred or a few thousand examples to do that. So you want this one-shot learning ability. Not everything can be learned that way, but a lot of things can be. We use a super high-performance knowledge graph. And when I say super high performance, we've benchmarked the knowledge graph that we've built against the best commercially available knowledge graph, and ours is 1,000 times faster, literally 1,000 times faster, because we've custom designed it for this purpose. So having a high-performance knowledge graph, it's actually a vector knowledge graph that we have, that encodes the knowledge and skills that the system learns. And it is able to encode it in a way that it can form concepts and basically work with that information conceptually. You can also add explicit ontologies. If you have external knowledge, so for example, in specific applications, you might have medical information or product information or whatever, and that can very easily be integrated into that knowledge graph. You know exactly where it needs to go. You have an upper ontology, and you can then plug it in, and it becomes reliable. So it's like having the RAG fully integrated into into the main model, if you want to look at it that way. So, if cognitive AI is so wonderful, shouldn't everybody be working on it? So who's actually working on that? Well, as it turns out, it's kind of an accident of history that almost nobody is working on cognitive AI. And when I say accident of history, it's the fact that the second wave of AI, the statistical approach, has been so successful relative to prior approaches that has taken all of the oxygen out of the air. Basically, it's the only game in town. It really has been super successful in speech recognition and translation, image recognition, and so on, relative to prior approaches. So all the money is going in there, and in fact, we are now in a situation where really anybody who studied computer science in the last 10 years or so, maybe 15 years, doesn't even know that there's anything else. When I talk to people like that, and talk about AI, AI, of course, it's statistical models, backpropagation, statistical models, big data. That's what it is. There's nothing else in AI, is there? So, if you want to do a PhD, you probably won't even find a sponsor for cognitive AI. If you want to raise money for a company, forget about it. Who knows anything about it? So it's really that there is so much momentum in statistical AI that it's taken the oxygen out of the air. Now we are seeing a shift. Now we're seeing more and more people realizing that large language models aren't going to get us to where we ultimately want to be, but there isn't any consensus or any clear idea in the community as to what the solution is, or that it might be or should be cognitive AI. So Intel have a research project that's very much focused on cognitive AI, elemental cognition. It's actually one of the original innovators of Watson, of the Watson product, who started the company Elemental Cognition. He has very much the same kind of ideas of cognitive AI. And then our own company, we've been building prototypes and then converting them and upgrading them to commercial products for the last 20 years. And so one of our big customers is 1-800-Flowers, Harry and David group of companies. It's about 12 companies. And they've been using our system for a few years. Last month at Valentine's Day, we replaced 3,000 agents that they previously struggled to, hire and train. So there really aren't many people working on cognitive AI. I wish there were more, because to me, getting to AGI is really the most important thing. I mean, yes, having more competitors is one thing, but there's so much work to be done to get to AGI, and I think the benefits are so great. So the path to AGI, I'll detail a little bit more of what we are doing, or what I think is a reasonable approach to make this tractable, because it's obviously a very hard problem. So the cognitive architecture I've already spoken about, with a difference. Super high performance knowledge representation is key to it. And the other thing that's sort of part of our secret sauce, not so secret, I'm sharing it here, is that all of the cognitive algorithms that we have, the learning algorithms, reasoning algorithms, whatever, memory activation and so on, all of those are custom designed to work with the knowledge graph and to work with each other so that the system is highly integrated. This is one of the shortcomings of previous approaches in cognitive architectures, where they've been very modular and really wouldn't work together effectively at all. When you're trying to make sense of a conversation, a sentence, it's not just a matter of parsing building a parse tree for the sentence. You really need to interpret that in the context of who you're talking to, what was said before, what is in short-term memory. You need to be able to use reasoning immediately. You might need to dip into long-term memory on what else you know about the person or the situation. So all of that has to work fluidly together to be able to make sense of a sentence. You can't just have a pipeline, text input, parse tree, and then try and make sense of it. It has to be fully integrated. So it's one of the things we've learned, discovered over the last 20 years. Another important thing is trying to find a sweet spot of what kind of roadmap will you have? What kind of milestones can you have towards AGI? If you started with robotics, seems like a reasonable approach. Build a robot, give it a brain, and then have the robot learn in the real world. That certainly seems like a plausible approach to AGI, because it can learn interactively working in the world. However, practically this is really, really hard and slow. If you have a physical robot, of course, to run experiments just is very slow, extremely expensive, and if you have any experience with it, or if you've spoken to anybody who's tried that, they spend 90% of their time fixing the hardware, and trying to get it to work. You could do it in a simulated environment, but that has its own limitations as well. So doing robotics, trying to have a simulated human or something like that is really hard. So what you want to try and make it somewhat simpler than that. What my idea is something that I call a seed AGI as well. You don't set your goal immediately on human level, full human level, adult level knowledge and skills, which is kind of the natural thing that people want to do now when they work on AI. They say, oh, we have to beat the benchmarks of ChatGPT. No, if you're no longer aiming for the most knowledge and skills that are in the system, but you are aiming for the ability to learn, and to learn incrementally, interactively, conceptually, then your goal is really, can we get to something like, call it a 9-year-old, 9-year-old human with not a lot of knowledge about the world, or whether it's 9-year-old, 7-year-old, or whatever, that can then learn largely by itself. So you get this sort of seed AI that you're really only focusing on establishing enough background knowledge, enough common sense knowledge, and all of the learning ability. And once you get there, then it really becomes just a matter of scaling up and training the system. So I think that seems to be the right approach. I mentioned already that we use a vector graph database, and the reason for that is that concepts are very important, a key part of human intelligence. I actually published a white paper, Concept is All You Need, the direct path to AGI. Of course, it's a bit overblown. You need a little bit more than concepts, but concepts really are key to human intelligence. What makes our intelligence so much different from animal intelligence is that we can form concepts on top of concepts on top of concepts. So we can have a virtually unlimited hierarchy of abstractions to end up with very abstract kind of thoughts. And a vector, the right kind of vector graph database is actually very useful for encoding concepts. I'll show you a little bit more about that later. So I've already spoken about this as a common structure of traditional cognitive architectures, with all the little blocks that really aren't integrated very well. Whereas our approach is, the knowledge graph that we have, the high performance knowledge graph, and then all of the cognitive components that work together, are integrated with each other, and are deeply integrated with the knowledge graph. So everything can work very effectively. Now, some of the tests we've done already, as I said, 1,000 times faster. We did a test against Claude 2. We haven't done it yet against Claude 3 to see if it's any better. Versus our own system, IGO system, in terms of being able to really remember and integrate a lot of things. Because our system can learn incrementally, and as it comes across new information, it integrates it into its, call it model or graph, this knowledge representation, and it puts it into the right slot. It can then use that information correctly. Whereas with large language models, you just have this this input buffer, but whatever goes into the input buffer is not structured, it's not integrated into the main model. And that is why, Claude did not do very well. We fed it about a few hundred pieces of information that it couldn't have known before, and then asked it a few hundred questions about it. And it simply wasn't very good at that, because it gets confused about what is in the buffer or how things relate. We also on our website we have an elder companion demo that shows something we achieved 6 years ago as a demo prototype. So, Who knows who this is?
Going to guess Helen Keller.
Hmm?
Going to guess Helen Keller.
Helen Keller, right, Helen Keller. So I sometimes refer to the way I think about AGI as the Helen Hawking model of AGI. So Helen Keller and Stephen Hawking. So I believe you can have very limited sense acuity. You know, Helen Keller was blind and deaf. And Stephen Hawking, of course, didn't have a lot of dexterity. So you can have a system that has quite limited sense acuity and dexterity and still be very smart. Now, our own approach definitely has vision, but you can still limit the amount of input that you have, because again, that's expensive to develop, it's expensive to train. You know, if you wanted to give it the kind of sense acuity that humans have, it's unnecessary for that. So that is sort of another approach, a design decision that we took to make the project, to make this whole project more tractable. So I put the 10-year-old. We don't know yet. You can't directly compare it anyway, because an AI's intelligence is, of course, ultimately is quite a different flavor from AI intelligence from human intelligence. So it's not a direct comparison. But we're basically looking at something, at some child level of intelligence, where you get to a point where it needs less and less supervision to be able to learn things, where it can learn more and more things by itself, where you have enough of a foundation of common sense knowledge, learning ability, reasoning ability, and so on, that it can basically bootstrap itself. And the approach that we take is basically it's an agent that lives on your PC, or could live on your phone as well, but let's say PC, has access to everything that's on your desktop, has access to mouse movement or clicks, basically can sense what you're doing with the mouse. And it can also use the mouse, it can use it as an activator. And then you also have a text channel, so you could be talking to it, text or talk, and it could talk back to you. So those are kind of the I/O channels that we've chosen to do, and I believe that's more than adequate to build AGI. Of course, on your desktop you can have an app running, a camera app running that's connected to the outside world. So there's only a small step then taking that brain and putting it into a robot. So let me talk a little bit more about concepts and why I believe they're so important, and just to concretize it a little bit. Very, very simple example here. So I can show the system a picture of a particular dog, and it can, get the features and learn the features of whatever features we extract from that, whether that's at the pixel level or some other format. And at the same time, we can input rover. And it can then basically create vectors to represent the visual information, and create vectors for the sound or the text input, whatever we do. And because they appear together, it can basically associate these two vectors and say, maybe there's something important, maybe there's some relationship between hearing the sound rover and seeing this image, and can learn that. And we can now repeat that with, different objects, with dogs, or, Excel spreadsheets, or whatever it might be that it can look at and learn. And it can now, one of the core capabilities, and what's so important, is to be able to generalize. So it can, now be exposed to a bunch of dog-like looking things, and then you could be showing it some, frogs, or roses or whatever, and they would be in different places in vector space, and it would be able, it can, I mean, we're doing that with our system right now, it can then automatically generalize and create what are the patterns of what a dog looks like as opposed to the patterns of what a frog looks like. And you can then learn that via unsupervised learning or supervised learning or self-supervised learning, where the system can somehow figure out whether it's on the right track or not through the results. But you can see the level of abstraction. You know, I went up to dog concept and then animal concept. Obviously, you can imagine now the hierarchy of different concepts. I've only shown the static concepts here, but the same thing applies for dynamic concepts, such as movement, you know, which are basically verbs. You know, the difference between a cat crawling or cat jumping or walking. And so those are different patterns, again, encoded as vectors and generalized. So, yes? Yes. Yeah. Yeah, that's an interesting question. Jan LeCun.
You start by repeating the question.
Yes. Yeah. So Jan LeCun recently made a statement that you know, children have trillions of bits of information come in through their eyes as they learn. And I forget what the numbers were, but you know, he took basically the bandwidth of a vision and multiplied that by the number of wake hours that, you know, a child has during development and what they learn. Now, and he claims that that's the amount of knowledge you would need to feed into, you know, an LLM or something for it to learn about the real world. Now, of course, the simple comeback there is, well, Helen Keller was very smart, and she didn't have any visual input. So clearly, I mean, she could touch things, so she had clearly a connection to the real world, you know, through three-dimensional world or four-dimensional world, three-dimensional world in time. And so she did have that kind of sense interaction. Now, how little information you can get away with in terms of training up an AGI is an open question. I don't know what the answer is. We are at the moment really getting the foundations of our system working. So we're working with very low resolution. You know, we have only a few dozen vectors in our system right now, but I fully expect it'll be, you know, hundreds or thousands, well, not vectors, talking about input features, not vectors, input features. So how little one can get away with to get to AGI, how little grounding you can get away with, it's not really clear. So I'm not going to go through this here. This is just kind of. I'll be sharing these slides, by the way. They'll be on the website because the recording of that you actually can't see the slides anyway. But these are the things that we are working through right now that are sort of built in. If you think about the difference between nature and nurture, you know, what do you actually have to kind of code into the system? What has to be there as to get everything going? And then what can the system learn? Basically building this knowledge graph, building these concepts, concept network. But these are things that we know that, you know, that we've already implemented, and we basically improving the basic ability. So yeah, that's pretty much it. All, you know, that we are we have a roadmap that we've worked out on what we believe we can get to the seed AGI stage, where it will really just require more scaling, where the system will already be able to kind of hit the books to learn. You know, to learn high school and then to go from high school to PhD level. Now, whether we're going to hit any walls along the way of things we really can't solve, that we'll hit some kind of scaling problem that we didn't anticipate, we can't get around. I don't think so with all the work we've done over the last 20 years, but we'll only know, when we actually implement it. And we're looking to expand our team. Currently, we have 10 people working on the development. That's apart from our commercial side of the business. And we're looking basically to scale up our team to 50 people. And obviously, if anybody here wants to help out with that'd be great. So, final thing is, why don't we have AGI yet? If what I'm saying makes sense, if cognitive AI is a solution to AGI, then it seems doable. That it seems that people should have been able to build it. I mean, I think if we had more resources, we probably would be there already. So there are a whole lot of reasons. I mean, the problem is, very few people in the world, and I talk about in the world, literally, because I go to the annual AGI conference, and this is sort of where people specifically focus on AGI, report what the latest thing is. Take DeepMind, for an example. I mean, even though they have 600 people, PhD levels, for working for 10 years, they're not really working on AGI if they don't have a plan to get to AGI. They're just doing research to figure out what to do. But you can't say that somebody's working on AGI if they don't have a plan to get to AGI. So, I spoke about how statistical AI sucked the oxygen out of the air. There's another very interesting thing, and I call it the narrow AI trap. And it's really a huge, huge problem. Anybody working on AGI, working on a general AI, if I work on something that has the intelligence or the knowledge of the 8-year-old or 7-year-old or whatever, I'm not going to be able to beat any benchmarks that are out there. So nobody's going to be impressed. Nobody's going to give me money. I'm not going to be able to publish any papers or anything because people say, well, what benchmarks can you beat? Can I play with it? Will it be better than ChatGPT? Will it have a better conversation than ChatGPT? No, because it doesn't have 10 trillion bits of information. Can I use it commercially? No, you can't put a 7-year-old into a commercial task. So there's a narrow AI trap that anybody working on AGI, and I've seen this over and over again, people who've really were dedicated towards building AGI and maybe even had some, pretty solid ideas, is invariably they ended up falling into the narrow AI trap where they started basically putting their intelligence and hard coding it into a system to be able to beat benchmarks, to have an impressive demo, or to have a commercial product, or whatever. And once you go down that road, it's really very difficult to recover. So another reason is that very few people in the field of AI today actually have a cognitive psychology background. It used to be cognitive science. 15, 20 years ago, cognitive science was quite a big thing, just basically the intersection between philosophy, cognitive psychology, and computer science. And I think it's that perspective that is really needed, that you need to be able to understand the problem from a sort of psychology point of view, and even epistemology, philosophy. What is free will? How do we learn anything? How can we be sure of things? What is our relationship to reality? What is consciousness? I think those are all pretty important things when you're trying to build a thinking machine, to have that perspective. So we have very few people basically entering AI from a psychology or philosophy background or being that way inclined. It's basically statisticians, mathematicians, logicians that are attracted to AI because that's where the action is. So yeah, that's another reason why we have so few people, why we don't have AGI yet. And, then we just have the usual thing of VCs, well, when am I going to get an exit? When am I going to get my 10x? And, it's just this sort of short-term thinking. People that might be worth, billions or tens of billions of dollars, but still, their whole mentality, their whole life, it's been about, making money or being able to look good by making a big donation somewhere or something. It's unfortunately a lot of people don't really have the vision of what the value of AGI can be and what it would really take to achieve that. Now, finally, of course, there are people quite legitimately who think AGI is a bad idea. And maybe one of these sessions I will focus on that because it's obviously an important question and I think a legitimate question to say, is AGI going to kill us all? Or even if it doesn't, is it actually good for humanity? Future shock, are we going to be able to cope with it? Unemployment, all of those kind of things. So, yeah, skepticism or dislike of AGI is obviously another reason. I also have an article on that. So that is my graph on the narrow AI trap. So finally, I really believe we are at a unique moment in history where ChatGPT has really given us a taste of what is possible. But we need to now have the right approach to do that. And my motivation is to get AGI to happen as soon as possible because I really do believe it'll be tremendously good for uplifting humanity, for increasing human flourishing and helping us cope with so many of the problems that are facing us. So, this kind of crazy money is being thrown at LLMs, hundreds of millions of dollars for seed rounds before companies even have a product or any revenue. Be great if some of that money actually went towards AGI. So, if any of you have an interest, what I'm trying to do here in Austin is to build a community of people who really are interested in AGI and to see, if we can create interest in that and either help our team to accelerate, but as I say, I'm really mainly interested in getting AGI to happen, so I'm very open to sharing what we've learned and really build a community to do that. So, that's kind of what looks like the field of AI. The AI winters we've had, I don't know if we're going to get another winter with the disappointment of LLMs, or if we're going to go straight into the third wave cognitive AI that'll get us to AGI. So my company, developing, commercializing, perfecting proto-AGI technology for more than 15 years. And we believe we can make a big dent in getting towards AGI. Thank you. That's it. So, questions?
I can just talk really loudly. Do you have any demos of this cognitive AI approach?
Yes. So, unfortunately, my journey in trying to develop AGI over the last 20 years, not months, has been derailed twice in the sense of falling into the narrow AI trap with my eyes open. So we would develop AGI prototypes that got closer and closer to where we wanted to be, and then we'd run out of money, and then we had to commercialize. So we had to dumb down the system to make it more robust, and then all the focus goes onto scalability, reliability, redundancy, and integrating, interfacing, and all that. So 6 years ago, we actually is when we pivoted last to commercial. But we have a very powerful demo from 6 years ago that's on our website. It's called the Elder Companion, where it can, learn things interactively and reason about things and so on. But we haven't really done much work on AGI in the last 5 years or so, because we've been concentrating on building our commercial business. Now, just 3 months ago, I handed over the running of the company, the commercial side, to my team, and I started getting back into spending most of my time on AGI. So we now have a new prototype that we're building, where I'm determined not to fall into the narrow AI trap again, provided that we can raise enough money to continue developing that. So our current version that we're building is not terribly impressive at this stage, So it's more on what we could show in the past. So it's really following the theoretical arguments that I've made and say, does this make sense or not, And then yes, we have some proof points in terms of demos we did many years ago. And of course, our commercial version as well, but it's really the plan going forward. That's
AI. I'm Franco. I run a translation company online. I'm just curious, why you don't never use the word neural? Are you denying the neural networks, or are you just consider them as statistical
Yeah.
models?
Yeah, why am I not using the word neuro or neuro? I think the term neural network has a certain connotation. Neural networks today really mean GPT. I mean, these days, or deep learning, machine learning. So that's why I kind of stay away from that. And the neurosymbolic, which I guess is sort of, what a lot of people are thinking about, is having a neurosymbolic approach, is very vaguely defined. And typically when people talk about neurosymbolic now, they're still very much clinging to, we're going to have this LLM, and then we'll somehow bolt on some symbolic stuff around that, and that will kind of solve the problem. So neurosymbolic itself, also to me doesn't sound right. But I always used to call what we're doing a neural network. I now just tend to call it a knowledge graph, but I think of it as a neural network. In fact, our code base in that we call them nodes and links. That the way we've implemented it. So I certainly see it as a neural network. But because neural networks, people immediately think it's backpropagation and big data, and that's not what we do. So, but I think of it as a neural network. It's hard to communicate, these things. Other questions? Yeah, so I implement vectors. It's actually a good question. So do we implement a vector knowledge graph, or? Yeah, do we use vector space? I'm not exactly sure what you mean by that, but let me explain and see if it gets it. So large language models obviously have vectors. They encode their knowledge in huge vectors. The difference of our approach is that the vectors that we use in our knowledge graph, so nodes in the knowledge graph each node in the knowledge graph is actually a vector. But the difference is it's not a fixed size vector like you have in large language models. The vector itself is ontologically based. So the dimensions of the vector should be meaningful and not just, statistical word correlations or something. So, I mean, you could see it, if I kind of really simplify it, the dog that I had there, if you have a vector for a dog, then some of the dimensions will be about the shape of the dog, some will be about the color, or the sound it makes, or whatever. So the vectors are of variable size, as required for what features you actually, meaningful features, ontological features you're trying to encode. Does that address your question?
It does. At least another question I was wondering. So we're wondering if those dynamic stat vectors, and how do you mathematical sense?
Yeah, and the vectors are totally dynamic. I mean, as the system learns, as it gets more information, I mean, it may, see a dog and not hear it, and then it hears the dog, so that'll add to the vector. So the vector size itself will also dynamically change. It has to. And then your generalizations are basically vectors that are generalized versions of that. All the different kinds of dogs that you've seen, and what the common features are of that.
Would it need to, so to prove that, like, if you have a bunch of dogs, right, and once they form a constant dog, right, so like Cocker Spaniel, Chihuahua, so each of those would have its own vector, right, and then once you get enough of them, you would have a new node to graph.
Yes. Yeah, you build a hierarchy, and basically you have instances of dogs, and they will be grouped or abstracted in the different breeds of dogs, but they'll also be abstracted in overall dog. And then, of course, the system can learn, that your neighbor has a dog, and that's maybe all you know, and then it'll be sort of the default or the most common properties of dog that you will assume until you know more, and then you might say, well, my neighbor has a brown dog or an angry dog or whatever, and then it will have a concept that has all the default dog features plus the specifics that you may know about it. So the system creates those vectors dynamically and updates them. Yeah.
I'm thinking about all those companies with all that funding that just do LLMs even more. So this is what's working, so we'll just do 10x that, 10x the results. So it seems like they would want to do some kind of risk management. It's 10x more of the same thing, really the best approach. They probably themselves aren't sure. So your solution seems like something they might want to bet 10% on. Does that make sense?
Yeah, so of course, when I list the characteristics of, what our system or what our approach can do, that it doesn't hallucinate and it can learn incrementally and so on, kind of the obvious answer is, well, can you not wrap this around an LLM and have all of the benefits of an LLM? And the answer is no, not really,
Yeah, what I'm saying is more like a risk management. If I'm investing in a project and I have 1,000 people to work on it.
Oh, you're talking risk management.
Yeah.
Well, of course. I mean, that's an argument we would have. If a VC puts $1 billion or $100 million into an LLM company, why wouldn't they put $10 million into ours? Well, of course, but you have to get to talk to them, and they have to listen for an hour or so to even remotely get to understand what I'm talking about and not totally dismiss it. And typically, rich people, have all of these layers of protection in front of them, and and they will basically say, well, what, this is not deep learning, what, this can't beat ChatGPT, and you kind of get dismissed out of hand. So you really need to have this sort of casual conversation like we're having now, where there's an interest of saying, hey, I might learn something here. There might actually be something new and different here. And maybe this has a chance, and maybe I should put some money into it.
I'm thinking more, not the VC level, because they don't really understand this, but the people they've already given $5 billion to, they might be aware that LLMs aren't guaranteed.
Yeah. Well, we're spreading the word, so hopefully we'll get some support for our approach. That, you know, it'll maybe make more and more sense as people really realize, like LeCun says, that LLMs are a dead end. You know, if you want to get to real intelligence. Yeah, another question.
Yeah, I have a comment.
I have a comment on your observations or your comments. I feel like the VCs and academics, whoever, people with companies, they're so invested now in the LLM approach that to even hear that it might not be the right approach is kind of, that's a hard thing for them to take. So I feel like that's the main reason you've invested billions and billions into this stuff and it might not actually be the answer. But the actual question I had was, how does this system that you guys have built, how does it understand the concept of a neighbor, the concept of having something? Does it understand on that level?
Yeah, good question. So how does the system learn abstract concept, you know, like, as you say, like neighbor, which is a relationship, or ultimately things like honor and so on. So we're quite unusual in our company that we have a third of our staff actually have a cognitive psychology and linguistics background. So we call them AI psychologists. So it's an invention. It's a profession I invented. So it's basically they're trying to understand how the mind of the AI works. And their task right now with the project we're working on is exactly to come up with a curriculum to teach the system these concepts, you know, the concrete bound concepts like, you know, dog, cat, or whatever we show it, house, car, you know, whatever. You have the concrete bound concepts, which are nouns, and proper nouns for instances, and then nouns for, you know, and abstractions of those. So that's reasonably straightforward. Then you get verbs, you get actions. So we show movement, you know, and how systems move. The next thing is prepositions, essentially, which are relationships. And so you have relationships of something is nearby or fast or getting closer or further apart or above or below, and time-wise before or after, you know, soon, those kind of things. So those are also still kind of concrete bound things. And then you have levels of abstractions where you apply those same patterns to, as you say, like neighbor, you know, somebody who's nearby and that you know. So the curriculum is to basically teach the system that layer by layer. And that's the big task. But we don't have to teach it everything. We just have to teach it enough that it can then start hitting the books, as I say, you know, so that it can start learning by itself. So that is the approach. But yes, there are really two very important aspects to our project. The one is to write the right code of the things that are nature, that are built into the system, having an effective knowledge representation, knowledge graph, and all of the learning and abstraction algorithms, short-term memory, long-term memory, all of that. That's the engineering part of it. And then we have the curriculum teaching part, which is just as important. So that's the kind of nurture part. You know, how do we teach it layer by layer, common sense knowledge and reasoning, the basics of reasoning. And that's very much what we're doing. So
Here, let me give you two statements and then a question, okay? So when we think about DeepMind, A, I'll make a statement. I believe they want to solve for AGI. Two, they know they're not going to get there with LLMs. So three, do you not think out of the 600 plus people that they have working on AI, they have 10 or something that are working on AGI, because they know, I mean, it was less than 10 people that came up with attention is all you need, which kind of gave this large, leap in AI.
Yeah.
So
I can actually, as it happens, I can answer that question actually pretty robustly. So first of all, the people they hire, they are selected for working on statistical systems because that's what they're trying to achieve. However, yes, they have enough money to say, shouldn't we be trying some other things? Now, the person in charge of the AGI development is somebody called Shane Legg. Now, Shane Legg, Ben Goetzel and myself coined the term AGI in 2002, and Shane Legg actually worked for me at the time. Now, Shane is a mathematician, and the reason he didn't work for us very long is our approach of sort of cognitive thinking about understanding intelligence didn't resonate with him. So he's in charge of the AGI effort, and in fact he recently published a roadmap, and it's basically more of the same, reinforcement learning, we've got to have bigger systems to train, we've got to have virtual worlds that we put the system into, but it's all big data. I mean, reinforcement learning is even more expensive than backpropagation,
Didn't you have his boss up here say something about we're not going to get there with LLMs, right?
Yeah, right. But they basically think they can bolt on reinforcement learning, and then that's no longer LLM, so more agents. So yeah, I don't, as I say, with Shane being in charge of the AGI,
They have people working on AGI. They're just kind of trying to improve.
Yeah, I mean, when you look at the roadmap that he published, it's really just. I was actually very surprised because it's not a roadmap for them to get to AGI. It's more a categorization. In fact, they're trying to do it like level 1, level 2, level 3. But that's just how will we know when we get there? And a lot of people in the AI field actually are focusing on the question of how will we know when we have AGI? And to me, that's not even an issue. Of course we'll know, but it's if you're working in the dark, if you don't have an understanding, if you don't have a plan to get to AGI, you will ask the question, well, how will I know when I stumble into it? Or are there some benchmarks we can build up, and then if we can keep beating the benchmarks, we'll get to AGI. But again, if you're facing that direction, it doesn't matter how hard you push. You're not going to get there.
But fair enough. So
Yeah.
I mean, I saw the chart that he put up, right?
Right.
And the analogy was, what's a fully autonomous driving vehicle, right? There's a defined and generally accepted concept of what a fully autonomous vehicle is. There's not one today, right? There's the 5 levels, and so he tried to come out with here are the 5 levels of AI, right? And to your point, for you to decide if you're going to get the AGI, you have to know what it means. What's the definition?
Right.
And in that chart, he tried to come up with what was the definition of AGI, and clearly said that we've achieved a really high level with narrow AI, but from an AGI perspective, we're still at almost like round 1.
Right.
So he at least acknowledges that.
Yeah.
Right? Did you say in his roadmap he's not?
No, there's no plan on how to get there. And there's a good analogy that we're facing right now with Tesla, with full self-driving. I love my Tesla. I had one for 6 years and tried to use the full self-driving. Just got a brand new one with the latest full self-driving, and no, it's nowhere near. There are just too many edge cases, and getting to level 3. Or even maybe level 4 in a well-mapped area, it doesn't mean you can get from there incrementally to level 5. You know, Elon Musk made the decision to totally abandon the rule-based system. You know, that's what the version 12 is about. It's an end-to-end neural network. I think that's a mistake. It's basically having a car that only has system 1 thinking. You know, you need system 2 thinking. You need, you know, something that says, hey, I'm not sure about what's going on here. I need to stop. You know, I need to supervise. But the architecture is inherently wrong. You know, so having a roadmap of functionality you expect, it doesn't matter if you get to level 3 in the wrong way.
Right.
You know.
But would you say, did you like his categorization? Because I think it's more defined than the DARPA categorization. The DARPA, at least there may be more behind that. I've seen this a couple of times, but it's pretty broad as opposed to the Google.
Well, the DARPA categorization, and why I like it, is it fundamentally addresses the approach you take to solving AGI, or the approach you're taking. Whereas the roadmap is sort of, the categorization is functionality, level 1 functionality, level 2 functionality, and so on. The point I'm making is, it doesn't matter if you get to level 3 functionality in the wrong way. You're still wasting effort. If you got to level 3 in the right way, you can get to level 4 or level 5. Or maybe you need to design a system that aims straight at level 5. You know, so I find those levels a huge distraction, actually. Yeah. The assumption is that you can always go 1 level up incrementally. I think that is kind of, and I think that's a mistake.
So cognitive AI, as you're describing, it's more to do with continuous learning, and then continuous learning, and then on a small footprint of system. So when you're doing this continuous learning, continuously improving the AI, what's the impact on not compromising system stability and reliability? How do you develop this without compromising system stability and reliability?
Without compromising system
Stability?
Stability.
And reliability.
Yeah. So the question here is that as the system learns incrementally, how does it not compromise system stability, basically? I mean, that is a difficult problem to solve, and the way we approach it is that you have layered levels of knowledge. So there are certain things that are just simply more fundamental in knowledge that you have, and therefore are more robust. Whereas if you try to teach all knowledge that has kind of equal weight, you can get instability and catastrophic forgetting and things like that. But if certain things are embedded much more strongly, and I mean that's basically the way it happens for us, you know, there are certain things that are just so fundamental that they will always override things that conflict with it. So that is sort of, in an abstract way, the answer to, you know, how you can get stability. But, you know, the system ultimately has to be sort of tuned and set up. What evolution did over billions of years, we have to do as well in terms of finding the right parameters of sort of incremental learning rates and things of that nature. But as I say, the fundamental principle that helps us get stability is the layered learning. You had a question.
I heard you contrasting this approach versus the statistic approach. I use Bayesian in a bunch of the work that I do. I'm rereading the book of Why, Bayesian and Causal Networks, and there's been about 100 years of conflict between Bayesian and frequentist approaches. One of the ways that they characterize Bayesian models or causal models is as a model-based approach versus a purely statistic and data-based approach. Would you say that this is also a model-based approach versus a statistic-only, counting things and using the highest probability only way?
Oh yeah, definitely.
Okay.
Not a model.
So is it, model-based or purely statistic? I sort of think of it, first of all, as a knowledge graph. That's really with different weights of certainty that you have. I've struggled to call my approach a model because the word model is so deeply tied to backpropagation and building models. When I talk to people, but I see it as a knowledge graph, a dynamic knowledge graph, really more than anything else. Do we have other questions, or sometimes people want to?
We talk about these concepts, right? It sees a picture of this one specific dog, and it's labeling it as a dog. It's building that concept of a dog. So, how does that specifically function? How does the model understand that without just labeling? Or another way to put it would be okay, it understands that these inputs are dogs, but how does it create an output that's a dog that's not just a selection from the training data?
So there's, how does the system basically know to output the word dog when it sees a dog? Is that kind of the question, or they make the association? Yeah. So there's an interesting story I always like to tell about Helen Keller. So in her biography, she wrote about what sort of internally we call the Helen Keller moment. Is she obviously before she gained language understanding, she obviously knew things, she learned things in the world. She formed concepts of, different things, chairs and tables she bumped into or avoided, and, dogs and cats and humans and different sounds. And so she had formed these concepts without words, without any language attached to it. And in fact, children do that too. And they initially learn these different concepts that they've seen. They've already identified them as concepts, but they don't have names. And Helen Keller, I forget at what age it was, whether she was 14 or 16 or exactly what age she was, but she got a sign language teacher to teach her sign language. And there was, after several months of this teacher trying to teach her what the signs related to, she reported later on in her autobiography, there was this one instance where she realized that the sign stood for a concept that she already knew. And the breakthrough was water, that she was shown the sign for water, and then she could make that connection. And once she had that breakthrough, she could now learn other signs and attach them to the different concepts that there are. And this is also when children have this language explosion where they learn 100 words a day or something. It's not that they learn 100 words a day. They already know the words, they've heard the words, they know the concepts, but they can now rapidly connect the word, attach the word to the concept. So in our system, we can basically teach the system concepts without words, or we can teach it the concepts with words paired together, so there's an association in the system. And you then have the word layer itself, which the pattern recognition of words as you feed in sentences, it basically extracts grammar from that. And that's basically the language itself has its own pattern and its own hierarchy of patterns and abstract patterns of how language works. But the language, in turn, each word in the language attaches to a concept that gives it meaning. So, in the graph, you basically have both the concept of the label for it, and you have a concept for the thing itself, and the relationship between those two. So it can then, basically, you can then teach it through mechanisms. We use what we call aping quite a lot, where we show it something. We would basically show it something, and then say fluffy, and then we do this a few times, and we'd show it something, and sort of prompt it to come up with something. And that's the most likely thing it'll come up with, is the name of the thing. But then we can teach it more sophisticated language where we can say what is or who is, and then if we say what is, it'll say dog, and if we say who is, it'll say fluffy. So we can teach it these different patterns of language on how how we expect it to respond to things. I don't know if it answers your question, but
Well, so like my understanding is when you speak about statistical models, it's doing that same process of creating like a generalized concept of something, and it does that through the means of statistics. And you mentioned like your team is working on programming this alternative method.
yeah. Well, there's a huge difference between statistical models. I mean, one of them is you can't get off the ground with anything less than 10 trillion words. I mean, that's when these models start working to be able to get those language patterns. Whereas, we can do that with a few million tokens or words or nodes or whatever. And it can't learn incrementally. Now, also, earlier on there was a question in terms of they're not really truly concepts of dog in a large language models. They are vectors that represent word co-occurrence. Basically, what are the words that are close to dog, and then at levels of abstraction. So it's not that it attaches the word dog to the visual input of dog or the description of dog, to the extent that that's purely accidental in terms of the word co-occurrence. So that's when I earlier spoke about the concepts that are embedded in our system are ontological. They're basically based on grounded reality. Whereas in a statistical system, they are grounded in word co-occurrence, basically. So that, and that causes a lot of the problems of that the system can come up with completely bogus things. I mean, an early example of that is when word to vector was still first introduced. Everybody was super excited that you could take the vector for king and subtract male and add female, and you'd get queen. So everybody was excited about that. But when you looked at that a bit deeper, we actually tried to use it in our system, and we found very quickly it wasn't actually that usable because, for example, dog and cat are closer in vector space than dog and puppy. So it's basically just in whatever you feed it in statistically, where is the word co-occurrence stronger, and not necessarily what is an ontological hierarchy that you really want to know.
Just building on this prior question, do you gift it a large ontology? Do you begin with the notion that there's an animal, and later on it learns that dog is in that category? Maybe you also tell it about dog, and that there are children, and that puppies are a child of a dog, as opposed to it inferring that based upon being.
Yeah, very good question. Do we start with a large ontology? It's a difficult decision because in our commercial product, we do start with a fairly large ontology because it serves us for the system to know a lot of things inherently, to have them in the graph database, and that we can use that information. However, we're not that concerned about them being grounded or what the exact attributes are and so on. So we do tend to put these these ontologies and just feed them in. But for our AGI development, we don't want to fool ourselves that the system actually seems smarter than it is. So this is again, I don't know if you were here earlier when I spoke about the huge difference between having knowledge and the ability to acquire knowledge. So intelligence is not having a lot of knowledge. So if you feed a huge database, a huge ontology into a system, the system seems smarter than it is because it can answer a whole lot of questions and so on, but it's just like database lookup essentially. So right now in our project, we resist that temptation, and we want to make sure that we focus on it being able to learn concepts in the right way, which is hard enough problem, and to learn language from the ground up. And in fact, that's the biggest difference right now in my AGI project that I started 3 months ago versus our commercial version. In our commercial version, our AI psychologists spend many months building language rules, basically, manually creating language rules. And the system is actually very, very competent. It's very successful commercially. But for an AGI system, that's not the way we need to do it. This was a shortcut for us to get to good functionality. For our AGI system, it has to learn language from the ground up. And so there are no rules being fed into the system. It needs to learn the rules by itself, the way a child learns grammar rules and conversation rules.
It learns physics from the ground up.
Yeah.
And it learns about the concept of concepts from the ground up.
Yeah. Well, the mechanisms to do abstraction, that has to be hard-coded. That can't be learned. At least we wouldn't know how to do that. So there are certain things that are, as what I would call nature, that's built into a system, like short-term activation. What are you currently focusing on? What is your context? What is your short-term memory, and the ability to learn patterns in time. So there are certain things that have to be built in. But yeah, the ontology one is something we struggle with. It's very tempting to just, hey, we can feed it 1 million words, dictionary and so on, and then it's really smart. But no, it's the wrong. Yes.
Can you try and sort of piece it together? You said the vector for cat and dog were closer than dog and puppy. And you're also talking about the, manually putting it in there to tell it which is what. What is creating that strength in the vector?
Well, it's not. It's the features. So they're basically similarities and differences that we're looking for. So again, remember that the vectors that we have, we try to have based ontologically. So that basically the dimensions of the vector reflect properties of the thing itself. And you then basically find out what are the properties that distinguish cats from dogs, and versus puppies from dogs. Now, obviously, puppies and dogs, there's a continuity of development. So, that's how we know a dog doesn't turn into a cat. Well, actually, children, when they grow up, they tend to put them in one bucket. I don't remember, and I don't know if it's cultural or where you grow up, but children initially call everything a cat or call everything a dog, and then at a certain development stage, they say, oh no, these things are actually different, So you then basically identify what features do you need to focus on to do that. And in our system, we can, of course, use supervised learning the same way you do for children. You say, this is a dog, this is a cat. This is a dog, this is a cat, this is a dog and a cat. And if you have enough of the features, the actual features representing these critters, then the system can basically work out from there. And that's built in, the categorization is built in to basically see how to divide the vector space to do that categorization. So it's not, it's not co-occurrence, it's not weight, it's not that you just need enough examples. And in fact, that's a big task of our AI psychologists, is to have very effective learning mechanisms. And we actually studied quite a bit of child psychology and how people learn most effectively. So what are the minimum number of examples you can show, you can show somebody to identify the key differences between the concepts so that you can basically, that the system can robustly do the categorization. I don't know if that answers your question. I think you at the back here. Yeah.
What are some techniques or methods that you could utilize to improve learning within a system so that it's comparable to like a 9-year-old, like you said?
Sorry, what? I didn't quite get that.
So what are some techniques or methods that you could utilize to improve the learning mechanism of a system so that it's comparable to that of a 9-year-old?
Well, the one slide I had was some of the core things, but what are the learning mechanisms that we do to get to this seed AGI? They're basically very primitive mechanisms similar to our neurons. I mean, there's no intelligence in individual neurons. It's really the ability to do instance learning, which is one of the important tricks that in machine learning, and that you don't really use. You abandon the actual instances. So our system does instance learning. When it has an input, it remembers it for as long as it's needed, because in a computer that's easy today. So you basically have the instances that are recorded of what individual things you've perceived, and then you have the generalization on top, but you can always fall back on the instances to recategorize. So instance learning is one of them, association learning, the ability to automatically do abstractions or clustering, and to form abstract concepts, to do the same thing with sequences, sequence of events, sequences of inputs that you have. So those are the built-in mechanisms. So it's instant learning, association learning, generalization. An important thing is using context. So basically, what is the context of what you're currently doing? What is the topic that you're talking about, or what was said before? That is also important. So, for example, when it's trying to give an answer, you might have been taught about two different dogs. It's always dogs, not cats. You might have been taught about two different dogs, but the one dog you've seen an association with Peter, and the other one you've seen an association with Paul. And you now see a dog, you can't quite make out which dog it is, but you've just been talking to Peter, so you assume you use that context for disambiguation. Of course, we also have reinforcement learning, that if there's an ambiguity and the system gives the wrong response, you can also say, good puppy, right answer, or bad puppy, wrong answer. So we have those reinforcement learning mechanisms as well. So a lot of these things are, basic cognitive psychology, which is, how brains work. Now, why today people aren't excited about that at all and kind of dismiss it, but that's too simple. That doesn't require GPUs, it doesn't require $100 million of training, it doesn't require 10 trillion tokens, So, like, what are you going to do with that? That's like boring, stupid, simple, And it's hard to break through that, when you're on the one hand working with these multi-billion-dollar efforts of big data. How exciting is it to work with something that's like 101 cognitive psychology,
That 2-year-old's too simple and stupid. What are you going to do with it?
Yeah, exactly. You're right. I mean, that is a real problem we're facing, until we get to quite a high level of, then people say, oh, what, this thing can actually learn by itself and improve its knowledge and ultimately get to do these things robustly. But in the meantime, yes, we can't beat any benchmarks, we can't build a commercial product out of it, can't even write any exciting papers about it, because it's not exciting. So you really have to have that vision, and you have to be convinced that you have to go that route, that big data backpropagation simply isn't going to cut it.
How closely are we
matching how humans learn, because there's space repetition, there's sleeping, and then information consolidates, and then also how long it takes to learn a subject.
Yeah, so that's an interesting question, is how close or how similar is our approach to the way a human works. And I think it's good to keep an analogy in mind here is, we've had flying machines for 100 years. We are still nowhere near reverse engineering a bird. So in the similar way, we are not trying to reverse engineer the brain. We are trying to implement the mind or the mental processes. And there are clearly a whole bunch of advantages that a computer has and disadvantages, of course, relative to a biological brain. So it's finding that balance of what are the tricks you can use. I mean, one of them is you can keep rebooting it and tweaking it. You can speed it up. You can run 1,000 versions of it at the same time. You can look inside the brain. You can use perfect memory as appropriate. The system can potentially reason much better, but it doesn't inherently have the sort of self-repair and redundancy of the brain, So there are pros and cons. So it's not really that similar. Early on in our project, we actually spent about a year trying to replicate Piagetian development stages. We thought that was a good idea, is to say, how do children learn? And I think there's something to it, the layered learning and so on. But we came to the conclusion that Piagetian development stages are really simply not appropriate for AI, because the basic infrastructure, your graph database doesn't change the way a child changes in development, or a child's brain changes in development. So we kind of abandoned that. So we try to learn what we can from neuroscience and from, child development and so on. But then we always have to say which parts are appropriate to incorporate and, how do we need to tweak them. I mean, we can, the system obviously has infinite patience, that it doesn't need playtime, or we give it specific playtime, And, I mean, sleep time, I believe you also need some kind of a sleep cycle mechanism where the system can rearrange things that it couldn't rearrange on the fly. So that's something else, but you can force it in the system. You can say, okay, we won't give you any input now. Go and, rearrange the concepts that you have in a more efficient way, or try and get rid of contradictions where you can. Yes.
What sort of similarities and what sort of differences do you have with Doug Lennon and PsychWork? What they've been doing?
Well, their approach was completely human-centered rules and ontologies, basically building everything externally. In fact, I spoke to Doug a few years ago, and he pretty much said that if he could start over, he would do it very differently. He would focus much more on learning, on the system being able to learn by itself, rather than employing, dozens of people to craft these ontologies that they did. But, he ended up basically selling the ontologies, and that's how the company could make money in whatever military or whoever he sold it to. So it's very different. I mean, it's basically their approach was all about trying to manually craft the knowledge graph, the knowledge base. And our approach is really almost completely the opposite. It's all about the system being able to learn these ontologies. Now, from the teaching point of view, of course, the curriculum we're building, that is, our ingenuity to come up with the right curriculum to effectively teach the system. But then the way it's arranged in the knowledge graph is really dynamic in the way the system integrates things. And the important thing is we want to get it as quickly as possible to a point where it can learn by itself. You know, the prototype we had 6 years ago, we already could point it at Wikipedia, which, you know, today is not a big deal anymore because ChatGPT does it in its sleep, you know. But 6 years ago, it could go to Wikipedia and read an article and integrate that into its existing knowledge base in real time. And you could ask questions about it and that. Now, there was a lot more work that needed to be done. It couldn't do that, you know. I think out of 10 random Wikipedia articles we picked, I think it could manage it well on 3 of them, you know. So we would have had to do a lot more work. But you know, as I say, that was fundamentally the wrong approach because all of the language capability was through language rules that we had put in manually into the system, the language understanding. Yes?
I'm just wondering, sometimes if we're going on the child analogy, sometimes things happen or learnings happen that challenge all the way down in the layers to the core truth. So if we're going on the dog analogy. Yesterday the dog was resting because it was tired, but today I learned my dog passed away. And so my core truth that dogs can live forever is challenged, but also my memory of the dog resting because of sleeping actually changes into it's resting because it was sick. So how does it go about, from like a vector perspective, of changing some of those things, and how does it become having layers down to go?
Yeah, so first of all, I guess we have the advantage that we can teach it about life and death sort of early on and you know, things like that. But yes, clearly there will be things that where it learns something that becomes invalidated. And that's an important part of the system. I mean, things change in the world as well. So it does inherently have the ability to relearn or to change information. And part of that is to be aware of the source of the information, because certain sources are more reliable than others. So if it reads something on Wikipedia or something, it would learn to what degree it should rely on that information, as opposed to what we teach it generally should be the ground truth. But then it also, as we develop the reasoning ability of the system, it will become more proactive in highlighting contradictions, things that don't make sense, and then it'll get into a stage of more like a child will say, why, or what? I thought it was this, and now you tell me that. What is it? And it might just be additional context that's needed, or it might be something that it somehow learned incorrectly at some stage. So that's a very important part of being adaptive. And yes, it can go down to the sort of the ground truth other than the stuff that's hard-coded. Yeah.
You mentioned in passing that there are a lot of people who are concerned about AGI that is in fact true, and I think for very good reason. Stuart Russell has written a lot about how you want to code these things to be intrinsically beneficial, and he's in a position to actually know what he's talking about. And he actually, I think, comes out of the intellectual tradition that you're working. Do you think that you can get to AI that is beneficial without the approach you're talking about? And if so, if that's, I'm sorry, if you don't believe that, then it would seem like that would be an important thing to focus on. It's not simply an approach to AI, but by the way, in AI, you might actually.
Yeah, so the question here is, I obviously believe that the cognitive AI approach will be beneficial to humans, but are there other approaches that are not likely to be beneficial, or that may not be beneficial, or may be dangerous? And you mentioned Stuart Russell. There's, of course, a whole industry on AI risk, and a lot of the misunderstanding is, again, there's sort of this background of mathematics and statistics, and somehow they've come to the conclusion that an AI is an optimization engine, and that it somehow has a particular goal that is coded in, and it tries to optimize to that goal. Now, I don't actually know any AI systems, you know, in the realm of ChatGPT or anywhere that are that. I mean, some narrow, clearly there are narrow, they're container optimization systems and so on. But to say to optimize for making paper clips or, you know, or making humans happy, that's quite absurd actually to think that it's just an optimization problem. Now, from obviously my presentation, I'm convinced, as I think a lot of people are, that LLMs are not going to get us to AGI. So therefore, they're not going to be smart enough to take over the world or really do bad things. Now, of course, they can fail in catastrophic ways. You know, I mean, we've seen miniature versions of that where this chatbot sold a brand new truck for $1. You know, so you can imagine that you could have disasters like that. And so LLMs, I think the biggest risk is that they're not smart enough. That basically they don't know what they're doing. So if they're deployed in the wrong place, they can certainly cause problems. But they are nowhere near smart enough to proactively cause trouble. You know, I mean, they would have to go through a whole number of steps to kind of defeat the various defenses that, you know, people will obviously put up. And LLMs, I mean, there's no way they can go through multiple steps reliably. I mean, that's a huge problem with them. So I see absolutely no risk of LLMs proactively being bad for humanity. I think, yes, they'll cause more problems because they're not smart enough. And now, so with a cognitive AI, we're talking about a system that is as smart as a human, at least, but has much better reasoning ability and doesn't have the emotional baggage that we have. So I wrote an article a few years ago that increased intelligence improves morality or makes you a better person. And the examples I give there is, the one very pertinent example is, if we go back to 9/11, it actually highlights very well, I think, human failings. The first thing is we tend to react emotionally. You know, we want to just, like, we wanted to hit back, you know, got to go somewhere, got to go to Afghanistan or wherever, you know, hit back. So there's this emotional response. The second failing is we make decisions with limited information. We often just look for, like, the first thing that resonates with us. Weapons of mass destruction, okay, we've got a reason, you know, that's good enough. We don't think it through properly. So with limited information. And the third thing related to this, we are not very good at thinking rationally, thinking through rationally. As I said, it's like an evolutionary afterthought, our ability to think rationally. Now, an AI will not hit out emotionally. It'll be much easier for it to gather much more information and be much better informed, and it's going to be much better at reasoning. So it'll avoid a lot of the things that, you know, mistakes we make because of our humanity. And, you know, it inherently, in terms of talking the risk, when people say, well, aren't AIs going to take over the world? I think we need to understand that what motivates us is very different from what will motivate an AI. An AI is built inherently to solve problems for us. That's what we build them. That's what we engineer them. That's the ones that don't do that don't make it to the next generation. The ones that help us solve problems, that do things we want them to do, are the ones that get built and get funded and get deployed. Now, what makes us tick? I mean, it's basically survival and reproduction. You know, and that's in our reptile brain. That's the core motivation. the AI is not going to have that reptile brain. We're not going to build it with a reptile brain. Why would we build an AI that has this core desire to reproduce and to survive? You know, so I think there's a lot of really poor thinking. I think they need an AGI to think about the problem of AI risk more. Yeah, another very interesting question about emotions and AI. There's a very good book called, what's it called now? It'll come back to me. I tip of my tongue, it's gone. Anyway, the idea here is when you look at emotions in AI, or emotions in general, it's actually, I think, there's a good way of categorizing or breaking emotions into two categories, saying there are certain emotions, call them emotions now for just use the word loosely here. There are certain types of emotions that I call cognitive emotions, things that are needed for cognition. Those would be things like certainty, confusion, boredom, and things of that nature that the system will absolutely have to have, and we have them in us. Surprise would be another one. So our system has that. It's part of, we call it part of the metacognition, part of the system two in a way. It's sort of a different part of the system two thinking. But it's basically the awareness of your cognitive state. So those emotions you absolutely want to have in an AI. But then there are the other emotions, you know, love and hatred and you know, and that kind of stuff. You don't want the system to actually have those emotions, but you want the system to be able to recognize them. So think of it like a good psychologist. You know, if you go to a psychologist, they need to be really good at understanding the emotional state of their patient without them getting involved into the emotion, without them feeling the emotion. So an AI can be very good at recognizing emotions and responding appropriately without it experiencing the emotion. You know, those are the survival emotions, you know, jealousy and stuff like that. So that I think is a good way. The book is called Affective Computing, by Russell and Picard, MIT. Yeah, I don't remember that she's written about emotions. Yeah, she may have, but I don't remember that. I do remember the Affective Computing book. I thought it was really good. All right. Are we exhausted yet, or do we have more questions?
I have dozens of questions, but I missed the talk, so I don't know what you said and what.
No questions?
I have dozens of questions. I just wasn't here for the talk, so I don't know where to start.
Well, please ask the question, and then, you know, we'll see where it goes.
Okay, so the AI, can it be competitive? I would think it can have an element of competition to it, right? The program or
It's a good question. Can it be competitive? I must say I haven't really thought about that as such, where that emotion fits in. I guess I see cooperation just being a much bigger feature. Probably my own thinking is more in terms of win-win situations, you know, than competing. I mean, I wouldn't want to waste CPU cycles on an AGI to win against somebody else, you know. It's a good question. I've not really thought about it.
Well, I'm thinking more of the sort of AI where you're not necessarily orchestrating it, so to speak, the sort of things that people are worried about. I'm not saying I'm worried about it. I'm just saying I'm a biologist by training, and I took learning and cognition from Rudolf Nonder, and so I know a fair amount about that sort of thing. Not a lot about computers, however. So I'm the artist you're going to be working with through Arctic World.
What is it?
I'm the artist you're going to be working with through Arctic World. I don't know if you
Oh,
know
okay.
about that.
Right,
But
yeah.
I just wonder about, you said something when I first came in that I was like, really? That it can't possibly get out of control. And evolution is part of AI, correct?
Well,
There's a learning.
yeah, I mean, evolution is part of AI. I think it's difficult thing to kind of say yes or no, because the term evolution is used, you know, so loosely in some cases. I mean, you have evolution of products, you know, like the iPhone evolves as it goes, but it's not the same as the kind of biological evolution that we talk about. So, you know,
It's not the same mechanism, but
no, it isn't. I mean, it isn't sexual selection, and you know, I mean, it is fitness within an environment, but it's you know, it's certainly directed evolution, if you want to use evolution. But yeah, I'm not sure that by itself tells us very much. You know, that yes, AIs will evolve in the very general sense. They'll become better and better, and we'll, you know, learn how to do them. But there isn't inherently, I mean, if we want to talk about fitness function of an AGI, I would hope it's entirely how good it is at helping us solve problems. I mean, that is, you know, the beginning of my talk was really about why we want AGI, and it's to help us solve problems, you know, to help us cure cancer, to have better energy solutions, to bring down the cost of goods and labors, you know, to have personal assistance and all of those things. All of those things are basically to try and improve human flourishing. So I would think and hope, certainly the work I'm doing is, that is the measure of AGI. How good is it at doing these things?
What would you say is the breakdown of how it's being used, AGI, in the world?
Well, we don't have AGI yet.
Well, I mean,
yeah.
artificial intelligence is definitely out there in many capacities. And just artificial intelligence in art, and it's right there, there's one.
Yeah, I mean, I'm really not talking about current artificial intelligence that we have, or don't have too much of an opinion on that. I mean, obviously there's good and bad, you know, that we use artificial intelligence in many things in a useful way, and there's a lot that's wasted and a lot that's negative, but that's why I want to move beyond that, of where we actually have true intelligence that can help us solve problems, and not just you know, rip off somebody or make a quick buck or something, but that can actually help us.
I really wish I heard the beginning, because true intelligence,
Yeah.
People are talking about emotion and compassion and that sort of thing. If you don't have those things along with the true intelligence, what?
Yeah.
Because there are a lot of super intelligent people who are doing bad things. I'm really ignorant about this, so.
Yeah. Well, we have a recording of it, so welcome to check it out.
Earlier on, you said something like the more intelligent you are, I think you had maybe
The more moral you are.
The more moral you are.
That intelligence fosters morality. Yeah, intelligence fosters morality, and I have on Medium.com I have an article on that. And the example I gave is we do a lot of things that we regret, and that's very closely tied to morality. Things that are bad, basically. I mean, morality is not what the church says, but it's morality doing things that are harmful and things we regret. And, the example I gave was 9/11, which I think is a very good example. We make decisions emotionally. We make decisions with not enough knowledge. We make decisions without thinking it through properly. And AIs will not suffer those limitations, or at least much less. So they will help us make better decisions, and they themselves will not fall into those traps that, are human limitations.
Right. Okay, so a human limitation is that I'm very, very aware of climate change and all of this. I still rode a car down here to this talk.
Mm-hmm.
AI would have us all just stop, which would be awesome, but I mean,
Well, you, of course, you're making an assumption here that driving a car makes a difference, or that climate change is a huge problem, or you're making that assumption, and
is already a problem.
well, right. So you're working from that assumption, and an AI would help us think these things through, and maybe the AI would come to the conclusion that we should all drive electric cars, or not drive cars at all, or whatever. But it depends what we try and achieve. So one of the things I would want my AGI to do is to compare, different risks that we have as humans, and benefits and priorities, and also do better research. I mean, for one, we know that the majority of research papers can't be replicated. We know that a lot of research papers have incredible biases from whoever's funding it. All of those things. So an AGI will be able to help us cut through that, and and say, well, this paper clearly contradicts, facts we know for sure, or these two papers contradict each other, and I can tell you why, and that'll help us a lot. And yes, it'll help us answer questions of whether we should feel guilty about driving a car to come to an AGI meeting. So it's having more intelligence available to us to help us flourish as humans.
So there is an assumption that humans are worth being the thing that is taken care of. Like,
Of course.
Oh, no.
Of course.
I don't know. I disagree.
You don't think you want to take care of yourself?
I think the Earth would be better off if there were no humans on it. I think I know what you're saying. I know what you're saying. I have children and all that. Humans, we just do irreparable damage. I don't see us turning it around right now. And
but even if we all die, the Earth is just going to carry on without us.
See, as a biologist, it just makes me cringe. All of the things that have evolved here,
I know.
and we are just destroying it at such a rate. And
but that's not inherent in humanity itself. It's inherent in the systems that are set up there to
Yeah.
structure humanity. Are you familiar with the teal model of organizing?
No.
So look at a book called Reinventing Organizations. Reinventing Organizations. Published in 2014.
Okay.
It's
Can you summarize the idea? Because
No, nothing to do with Peter Thiel. This has to do with a new stage of human development that's currently not being distributed widely across our society.
I think.
But it profiles 12 organizations currently in
Mhm.
operation, 12 companies that are operating on this level of self-management, fullness, and evolutionary purpose, which doesn't accord with present systems now.
Yeah.
But if it is adopted, you won't see the destructive systems currently.
If it is adopted, is it a long-term strategy?
Absolutely.
That's
for
the problem.
sustainability.
I love it. I want it. But that's the problem.
Reinventingorganizations.com.
Yeah, I don't think we're gonna have time to get there.
Peter, regarding the safety issue, if these things have metacognition, are they able to rewrite their code? And do they have a sense of agency?
Yes, of course, an AGI will of course have, it'll be conscious. It'll have to be conscious. It has to be aware of itself as an agent acting in the world. It needs to know what it is responsible for making happen as opposed to other agents in the world. So absolutely it has to have agency. And of course, it can train itself to be a programmer, it can train itself to be a computer scientist. So it can, in fact, that's one of the other ways of looking at seed AGI, is that once you have the first AGI that's smart enough to understand its own code and its own design, its own architecture, then it'll be able to improve on that. So, that it's a sort of an automatic byproduct of an AGI. And
Not necessarily regarding your AGI, but anybody's AGI or whatever AGI it progresses to. What's to ensure that it's going to be aligned with healthy human objectives?
Well, I have a problem with the whole thing of alignment, because what is it aligned to? It's what. Yeah. I mean, if we deploy AGIs to help us solve problems in the world, it will help us to identify these problems as well. To me, the reason to build AGI is to improve human flourishing, to improve human well-being, and if that is the goal, it will be able to do a better job of that than humans trying to figure it out.
Yeah, I mean, the system that humans have set up, governments, is inherently not in line with human objectives that are based on flourishing. It's more about short-term interests and dysfunction from a systemic standpoint, dealing with ecosystems. I mean, the U.S. military is the world's biggest polluter, so it's going to see that as problematic. And then humans are not going to want to change those things, the ones that are running those systems. So you can see the conflicts arising there with the certain objectives of these AGI systems. You can see things more clearly, logically, versus the humans that are running these other systems that are kind of off the rails, right? So then the question is, how does resolution happen without problems, right?
Yeah, I guess it'll depend on how stubborn humans are against listening to reason.
Look out.
What if the reality was, or the truth was, that some group of people, some whatever, needed to be exterminated or whatever? Maybe that was the truth, and this AI figured that out. Like, these are the things that this is what I can't reconcile. Like, if it becomes super intelligent and it figures out something that we just can't accept, what are we going to do then? And then the second thing is, like, is there anything that stops it from, you say the purpose is for this technology to help people. What if this person or people want to use it for nefarious purposes, but it's useful to them and very helpful to them? What's to stop that? What's to stop the AI from helping?
Yeah. So two answers to the question of how can we protect ourselves against people who want to use AGIs in a negative way. So the one is, you obviously have to hope that there are more good guys and bad guys around. People who want human flourishing and that, and then you will have more AGIs working to protect, or to protect you against the bad AGIs. So that's basically the same situation we have with humans. But there is actually another deeper philosophical thing that I studied for quite a bit, and that is what is morality based on? And I think morality should be treated like a science, that you can figure out what principles actually work in the real world, what principles work in the real world to, ensure flourishing. And that philosophy, if you go down that path, you actually find that there are universal principles dictated by reality. For example, like lying is less effective than telling the truth. Cooperation is more effective than, dog-eat-dog competition. So these are universal truths in reality, and an AGI will understand that those principles are simply more effective to do. So the AGIs that somebody tries to subvert and use to lie and cheat will inherently be less effective, because reality gets in the way. You can only fake reality for so long, and then it kind of catches up with you. Unfortunately, you can fake it for quite a long time, as we see. But again, I see AGI with each of us having this personal assistant will help us also realize who are the good guys and who are the bad guys, and why.
This is all science that's just in its infancy because women have gotten into science. It used to always be aggression and dominance and blah, blah, blah. But it does, and we've seen it with Trump came to power because it takes a single hawk to get the other hawks going, and a system that harbors and lets fester real problems. I just wonder, since we're so fallible and so bad at doing this, how are we going to have a computer program be any more successful? I'm really...
Yeah, absolutely, inherently, because it doesn't have the limitations of our brain. It doesn't have these emotional responses. It's much better at thinking clearly. It's much better at taking more facts into account. It doesn't have its own agenda, its own ego. It doesn't have the need to belong to a tribe. These are all the kind of things that tend to mess up our lives.
So the good ideas are there, I think, already, but people are people. They're stubborn, they're set in their ways. So what do you do about the people that are standing in the way of it right now?
Well, when people start relying on AGIs because they are so helpful, they will also start to listen to their advice because they'll find that this actually helped me. AGI will not only be your butler that will do, deal with the IRS and with your insurance and stuff like that, but also you can bounce ideas off it and say, should I get into this business relationship here, or should I break off that relationship? Should I, and it'll help you think things through. And then political issues as well, it'll be able to give you an objective analysis, and you may like it or you may not like it, but it's going to be rational and, not get passionately carried away. And
Part of it, because there's an art to it.
Yes, yeah. They should be good psychologists as well, yeah. All right. Should we wrap it up? Okay, we need to wrap it up. So we need to put this back into the shape it was when we came. So I don't know if there's any stuff. Well, thank you very much, and thank you for those of you sticking around here.
So, global warming.
Regarding pathological science, right? I feel that to your point about the earthquake.
I thought that was what the talk was about, is art and AI and art.
The art of persuasion and the art of persuasion. I do anecdotal friends. I used to have friends who lack the social consciousness, right? Has no kind of sense of remorse, or hurt people. Nothing you can't see it. But when he does it, there's no response. However, I have been able to, over the course of like 10 years, get him to see if you engage in exploitative tactics and manipulation and cause harm, that will actually disrupt the environment, and that will not even affect the development. So it is possible. So I think that is what maybe a case study. Maybe the whole future.
I've changed lots of people's minds on real hard things because I do have that. It's not easy, and it takes one-on-one interaction.
I believe it was, I believe it was,
Yeah, I didn't know you wouldn't ask me, but my issue is like, how do you scale that? Like, how do you scale my one-on-one interaction with my friend, right? It's like, like constantly, like, angel on the devil shoulder kind of thing. I could imagine that. This is a war on it, not that.
Right. But, like, that's exciting.
Well, I'm definitely interested in like learning more about this space and helping out. I'm not necessarily expert over anything.
However, you'll have a document in your position. Okay, that's science, and that's something you should learn. Why don't you listen to people who are equally knowledgeable about climate change? There's no cross. The cognitive dissonance is their favorite place to live. And so,
These top guys say, LLMs are not going to get us there. And they don't give us clear alternatives.
They are very,
they are lacking the cognitive approach.
sure.
You know, they are statisticians. And they're always so successful.
This demo is a very impressive.
That role, that person can, it's not enough, it is hard to talk about. It would almost have to like kind of befriend them, right? Once you kind of get close to friend, then
What about all the
irrelevant
nonsense and trash information?
the groundwork.
With our organization, actually,
yes,
a
but
lot of this.
the groundwork is to be scattered. The doctor,
Right, you can't just close that. Oh, you're talking about some kind of external system that can go and check currency. I think because it's each model is permanent. That's the thing, it wouldn't even be able to know if it's hallucinating or not because we would have to fact check. I think we'd have to fact check on some external source, or it would have to be architects original. So we would go like the internet and we would go to the right? Say like if the system should include something like outside of it. Not inherently, whatever solutions are super slow. Like you could ask go to the internet and you're looking at the article and you have no way of fact checking that, you know, whether it's real. I honestly think it is. That's very expensive. Maybe that would make sense. I don't know, I just don't see that approach. Yeah. I just don't see that approach working because there's like a trick to it. You get all the information in the world, you use all the information in the world, and it's still the data for the next step. And I don't think it's what we do. Some people argue that it's what we do. I don't know, I just don't see it. People are working on it, and I mean, I'm curious to think of other solutions, there's just so much high money. We're not seeing the results. We're just not.
Why would it be that?
Next prediction. So
you got the money. The money.
You would have to predict the next token for a very intelligent
why would that be? Down to where properties and getting up this kind of a pretty sharp
in hindsight now, you can see why. Because it only can output something that's in the training data. If it's okay, yeah, it reminds me of the bus, yeah.
And people are satisfied.
But so far, we've been able to see that it only works really well on things that are in the training data. So if you go and ask it about something, you know for sure it's not in there. It will release. So if it's based off of if it's based off of the information before the snapshot, we haven't been able to see it generate anything that would be that comes after the snapshot, even if it was like based off of, you could say, okay, say to come up with a topic, the cutoff is April 2023, but May 2023, based off of that knowledge, another thing was found out of some kind of innovation. The LLMs will not be able to predict that because that's just the next organization. And I guess the argument is like you just have to really good stuff is going to be able to reason its way. More compute is going to be able to reason its way to this new knowledge, but it's just